Okay, hello everyone. We are on for our last video of the semester, part 2 of chapter 17. So in this video, we're going to finish up our discussion of radioactivity and nuclear chemistry. We're going to talk about the rate that these nuclei can break down. We'll call that nuclear decay. We're going to talk a little bit about how we use this to determine the age of something with carbon dating. Or we could also determine how much mass of something is left after a certain period of time, after how much we would have expected it to decay. So, what do fossils in Wisconsin, Tutankhamun, and the Dead Sea Scrolls all have in common? Well, they all contain our favorite element, carbon. While our discussions of radioactivity and nuclear chemistry may have been a bit chaotic so far, we're talking about all of this bombardment and fission and things breaking apart and fusion and things slamming back together, emitting this energy and radiation and stuff like that. There are a little bit more stable facts that we can use about radiation, how it occurs, and at what rate nuclei emit these radioactive particles that we can leverage. And we can use that to date artifacts from the past. So we've learned the age of all of these different artifacts through what we call radiocarbon dating, which we'll talk just a little bit about in a minute here. So, what do I mean radioactive decay? I've been kind of avoiding using this word a little bit in part 1, but we've been talking about how in nuclear reactions and in radioactive emissions, we have these small particles that are emitted from a nucleus. So we're going to give that process a name. When we have a nucleus that's going to emit something and become another kind of nucleus, we're going to call that radioactive decay. So each isotope that is radioactive kind of works its way through a relatively predictable series of nuclei on its way to becoming stable, working its way kind of down to what it's going to decay into. So each of these steps in the decay process happens on a relatively predictable time scale, so we can predict relatively well how long a sample has been decaying for based upon its makeup. So we see the decay of uranium-238 here. So here we'll see the different kinds of decay. Remember we talked about alpha particles and beta particles. You can see the different arrows labeled here. Red for alpha, blue for beta. So remember, when we have that alpha decay, we're going to change the identity of our nucleus big time, because we're going to emit 2 protons, 2 neutrons. And then in our beta decay, we have a neutron becoming a proton, and then we're emitting an electron as we're doing that. So that's kind of what we got going on here. In all of our different identities as we go down. So it may become different things at different times, but again, these are relatively what we would expect to happen. We'd go from uranium-238, and where it usually ends up stopping at here is lead-206 in the end. So that's an example of that's an example of how they will decay over time. So, let's talk a little bit about kind of what some of this means and radiocarbon dating. So through observation and experimentation, scientists have been able to determine an approximate time that it takes a specific isotope to decay. So different isotopes take different amounts of time to decay, and we can determine that approximate amount of time that it takes for a certain amount of the sample to decay into something else. So, for example, you can kind of see a graph over here depicting the decay of thorium-232. So, we use this value called a half-life. So, a half-life is the amount of time it takes half of a sample to decay. So, this is like a measurement of the number of decays over time, and we choose to use the half-life because it's something that we can use a lot of the information from to determine kind of where things are going along those lines. So some isotopes have a really, really short half-life, and they decay really, really quickly. However, other isotopes have a really, really long half-life and decay slowly over time, and they take much more time to work their way through the whole sample. So here's a list of different half-lives of selected nucleotides. So the half-life of thorium-232 is actually 14 billion years. So if you had a sample of 1 million atoms it wouldn't even be fully decayed by the time you had reached, like 60 million years there. 60 billion years there. So it takes a really, really long time to decay. However, Radon 220 here only has a half-life of 55.6 seconds. So if you had a smaller sample of that, it'd be gone just like that in the end. So we can kind of use the information we've learned about how long these half-lives are in consideration of some of our scientific choices and which kind of which isotopes we might use in certain situations. However, what I want to make sure you know here is that things don't just decay to 0 atoms after 2 half-lives. So a half-life is always half of what is there. So half of 100 is 50. Half of 50 is 25. Half of 25 is 12.5. Half of 12.5 is 6.25. And so on and so on and so on. So when we're saying it takes a half-life is the amount of time it takes for half of the sample to decay, you kind of have a new sample size every time a half-life occurs, so on and so forth. And on and on and on. So, what does this mean for us, and why do we care about half-lives? Well, we use it when we talk about radiocarbon dating. So radiocarbon dating uses the half-life of carbon-14, a radioactive isotope of carbon, to determine the age of an artifact based upon how much carbon-14 an object has compared to like kind of currently living beings. So when you eat and you breathe and you drink things and you're interacting with the environment, you're constantly replenishing the amount of carbon-14 in your body versus what might be decaying away. But when you die, sad day, you stop adding to your sample of carbon-14 over time. So the decay process can be measured to date the time where you stop taking in more carbon-14, either the date of creation of an artifact, or if we're talking about a fossil, the day the fossil kind of stops living then. So like if we were thinking about those tree fossils in Wisconsin that I showed you on the first page, we would know when that fossil actually stopped living because it would stop taking in more C14 at that time. If we're talking more specifically about carbon-14, for example, we can kind of compare the age of an item to the amount of carbon-14 you have left. Again, in a currently living organism, you would have kind of the age of the object, therefore being 0 years from the date of that endpoint. So that would be 100% of a C14 sample. So again, we're always going to compare to kind of what that living organism or what a freshly drawn sample would be. And then the half-life of carbon-14 is 5,715 years. You're going to become very familiar with that number in just a second here. But it's 5,715 years. So it's also why it makes carbon dating kind of relatively useful for us, because it has such a long half-life that we can measure these samples and we can kind of go back years and years and years and still be able to represent or find pieces of carbon-14 in these samples and measure those amounts of carbon-14 in the samples, because it does have a relatively long half-life, but not so long that it's kind of immeasurable in a way like that half-life of thorium-232 being 14 billion years. Obviously, we're not going to see half that sample decay in 14 billion years, because humans haven't even been around for 14 billion years. So, again, we could use proportions and things like that, but using things like carbon-14 being in lots of living organisms and having comparable samples to draw from, it makes carbon-14 really, really useful when we want to date certain kinds of artifacts. Again, so if we've gone through one half-life, that means we have 50% of the sample left. So that means we can kind of assume the age of the object is around 5,715 years. If we can kind of compare the two values, and we can see that we have about 25% of the sample left, well, that means it's probably about 11,430 years old then, for example. So, that's kind of what we got going on when we're moving through these different kind of percent relative to the living organisms. We're seeing each half-life, and after how many half-lives would be how many years, for example. So this would be 1 half-life, 2 half-lives, 3 half-lives, 4, 5, and 6, and so on and so forth, down and down and down into smaller amounts of half-lives. So we're kind of using this information that we figured out about carbon-14, that it has this half-life of 5,715 years, and we can kind of create some equations and information to calculate either how much mass remains in our sample, or if we know how much mass would be kind of in a comparative living being or a freshly drawn sample, compare that to how much mass remains, and then we can figure out how many half-lives have occurred, and if we know the half-life, well, then we can figure out the amount of time that has passed since that kind of end point where the sample of carbon-14 stopped increasing because either, the tree was cut down, or, a piece of cloth was made from freshly picked cotton, or, when Tutankhamun passed away and stopped taking more C14 into his sample, for example. So I've given you 2 equations to describe these 2 different situations. So I don't want you to have to solve for complex variables, so you will just need to choose the appropriate equation based upon what the question's asking you. So you'll use the top equation here if you want to solve for how much mass remains in a sample after a certain amount of time. Or you'll use the bottom equation down here if I'm asking you how old something is, and I give you 2 different masses indicating the original amount of mass and how much mass remains. So what you need to know is really what I mean by the number n in these equations, okay? How much mass remains, original amount of mass, those are pretty straightforward. However, n is the number of half-lives that are completed. So if I give you, for example, an original amount of mass, I give you an amount of time passed, and a half-life amount, you can calculate that n, that number of half-lives that have been completed, and you can plug it into your equation here. So you may have to first determine that number of half-lives completed, plug it into your equation, or if I give you the original amount of mass, I'm asking you how many years have passed or how old something is. We could compare the original amount of mass compared to the how much mass remains, and then that will give us the number of half-lives that have been completed. But if I'm asking you for a number of years or something like that, remember, I'm not asking for the number of half-lives completed, I'm asking for the amount of time passed, so you may have to multiply that by the half-life down here. So this is kind of a little abstract for right now, but we'll do some examples so that I can show you what I mean, how you're going to use these equations in the end. Okay, so we're going to go ahead and work through the first example you see on your screen here. So this question asks how much mass remains in a 125 gram sample of C14 after 28,575 years, and it lets us know that the half-life of C14 is 5,715 years. So what we're going to do here is first, as always, write down what we're given, and then we will write down what we're looking for. So here we are given that we want to know how much mass remains in a 125.6 gram sample. Well, that's going to be our original mass. And then we're told that how much time has passed is 28,575 years. And then we also know that the half-life of C14 is 5,715 years. And the question asks how much mass remains. So what we're looking for is how much mass remains. Okay, So we're going to go ahead and use that first equation from your resources that says how much mass remains. I'm just going to abbreviate that to like how mass equals 1 divided by 2 to the n, and that's times the original mass. Sorry, I'm running out of a bit of space there, so see if I can't scoot that over a bit. All right. Again, we're going to take the how much mass we're looking for is 1 divided by 2n times our original amount of mass. Well, remember, we do have to figure out what that n is. That n value is going to be our number of half-lives. So we'll take the amount of time that has passed, and we're going to divide that by our half-life. So that means we have n equals 28,575 years divided by 5,715 years. So our n in this case is 5. So our n is 5. So this means that 5 half-lives have passed. So now we have all of the information we need to plug into our equation written up there. So we're still looking for how much mass remains. How much mass equals 1 divided by 2 to that n value, which here is 5. And our original amount of mass given in the problem is 125.6 grams. All right, so we'll just go ahead. We will type that quickly into our calculator, and we'll know how much mass remains. Always making sure we're keeping the proper number of significant figures. And we're only going to worry about the significant figures given in our problem. We're not going to look at the sig fig given to us by that n value. It's just a calculation along the way for us. So in my calculator, I'm going to type 1 divided by parentheses 2 to the 5 and enter. And I get 0.03125, and I'm going to multiply that by 125.6 grams. So in the end, I get how much mass remains is 3.925 grams. It looks like this number here has 4 sig figs, this number has 5, this number has 4. So I'm going to go for 4 sig figs. 1, 2, 3, 4 sig figs in my answer. So I'm going to call it good. My answer is 3.925 grams remains in this sample after 28,575 years. So that's our first example. Again, as you're working through these problems as well, you may have heard me say a few things out loud about how I was typing this into my calculator, but I do include photos of my calculator screen here on the slides as well. So you can see this math worked out in a bit more neat of a manner here. And then you can also see how I personally typed it into my calculator as well. So let's go ahead and do example number 2. Example number 2 asks us, how old is a fossil of a plant leaf if a leaf of a similar live plant contains 30.25 grams of C14 and the fossilized leaf contains 7.563 grams of carbon-14. And it reminds us that the carbon or half-life of carbon-14 is 5,715 years. And remember, this asks us in the end for a number of years, not a number of half-lives. So we have to make sure we get to years in the end, and we're not just reporting that number n of half-lives. So again, first and foremost, as always, let's do and figure out what we're given. Read through the problem and figure out what we're given. So given, so how old is a fossil? A similar live plant contains 30.25 grams of carbon-14. So this is going to be our original mass, okay? So we're comparing to things that are alive, things that are happening today. Anything we're talking about alive or freshly picked or something like that is going to be our original mass. So original mass is 30.25 grams. And then it tells us that the fossilized leaf itself contains 7.563 grams of carbon-14. So that's going to be how much mass remains. Let's call that remaining mass for right now. How's that sound? We'll call it remaining mass. And then it reminds us that the half-life of C14 is 5,715 years. And then we want to know what we need. Well, what we need is how old is that? So we want to know the amount of time that has passed. How old is this fossil? So in the end, we're going to use the second equation that we saw a couple of slides up. So that tells us that N equals the log. Remember, we've used that before when we were talking about our pH equations. Logs come back. We're talking about fossilized plants, and I'm talking about logs. Math jokes. But we're going to take the log of the original mass divided by how much mass remains. Again, we're calling that remaining mass for right now, for brevity. Let me scoot this over a bit. I don't know why I started so far over. Remaining mass. Oop. And we're going to divide that by log of 2. I got the logs in how I solved the math problem, so don't worry about how we got here. If you really would like to know, come meet with me. I will show you how to solve these math equations, but the information that you're given here, don't worry about it. Just know how to use these equations, right? So remember, we're solving for N, and N is the amount of half-lives. Once we know the amount of half-lives and we know what the half-life of C14 is, we can figure out how long or how many years this fossil has been around. So let's go ahead and plug into our equation. We can say that N equals the log of the original mass, which is 30.25 grams, divided by the remaining mass, which is 7.563 grams, divided by the log of 2. So I'll go ahead and type that in my calculator and see what I get. So I'm going to type log of 30.25 divided by 7.563. And then I'm going to hit divided by log of 2. Remember, if your calculator's automatically putting those parentheses in, make sure you close your parentheses. If not, take the log of the top, hit enter, take the log of the bottom, hit enter. So I'm going to go ahead, I'm going to take my logs, and what I get is 1.999904618. So here, I just want you to round to 2. So this is approximately 2 half-lives, so we're going to say 2. Okay, so we're going to use our N equals 2, and we know that the amount of time that has passed equals that number of half-lives times the half-life value. Half-life. So here we would say that the amount of time passed, amount of time equals 2 times our half-life, which is 5,715 years. So we can say that the amount of time is 2 times 5,715, and that gives us 11,430 years. So 11,430 years as our answer. Of course, we have to go back and triple check our sig figs. Here I have 4 sig figs. Here I have 4 sig figs. Here I have 4 sig figs. So if I look at my answer, I have 1, 2, 3, 4. That 0 does not count. It is not sandwiched by either a decimal point or another number, and it comes at the end. That 0 does not count. So I have 4 sig figs, so 11,430 years is my answer in the end. So, again, if we're talking about those number of half-lives, please don't use that long stinking number in your calculator. You're probably going to get the answer wrong. It's not what we're going for here. If you get 1.99999, that's close enough to 2. We're going to call that 2 half-lives, and then we can use that as our n value to plug in. So you're always going to get something that's either actually a certain specific number of half-lives, or you'll get something that's like very close to another number. Please round that before you use it to a whole number. Your number of half-lives should always be a whole number here, okay? So, that being said, I have given you, again, a more neatly written version of this. Again, I show you we're going to round that 1.99999 number to 2, and then we're going to use that n equals 2 value to determine the amount of time passed. And I give you my calculator screen here as I worked through this. I've given you 2 practice problems to work through as well that are, again, very similar to the examples I just gave you. And I give you my calculator screen there as well. So go ahead, please practice with those. They'll be very similar to any problem I give you like this on the exam. So that being said, that's the end of chapter 17, and that's the end of our content for this course. So thanks for sticking around with me. I hope you got to the end here, and yay, we did it!